Okay, under new findings in cyclones, I'm going to add this paper from Vineet Kumar Singh and Matthew Cole, Roxy Matthew Cole, a review of ocean-atmosphere interactions during tropical cyclones in the North Indian Ocean. So it is a review article, so they go through some of the previous results to summarize what we know about ocean-atmosphere interactions, starting with this nice figure from Clément Montague de Boyar's paper from 2007, which shows pre-monsoon SSTs, post-monsoon SSTs. We know that during the pre-monsoon, when you are coming out of the winter monsoon into southwesterlies, winds are not strong yet, so the Arabian Sea hasn't cooled yet. So you will see a fairly significant warming, even though the coastal winds do show some upwelling and cooling over here by a couple of degrees, and the Bay of Bengal is not started convecting yet heavily either. So Bay of Bengal remains warm anyways, but you can see during the post-monsoon both of them cool down because the northeasterly winds begin to pick up. Dry continental winds begin to increase the heat loss, and associated with these you can see the salinity here. So upwelling brings more salinity, and the Arabian Sea is more saline anyways compared to the Bay of Bengal, which has as much freshwater forcing as precipitation, and the peaking of the river discharge tends to happen during the post-monsoon season, as you can see with the reduced salinities here. This leads to some differences in the mixed layer depths as well, but this is a diagnostic study. You have to be careful about how it is defined. Here it is defined as change in the density of 0.03 kilogram per meter cube. So it also doesn't capture the inversions that are very common in the Bay of Bengal in terms of vertical temperature gradients, which also affects calculations of barrier layer thickness. If you remember from our other courses, barrier layer is basically the difference between the isothermal layer and the isohaline layer, or the density layer. So you have a barrier layer, which means when a cyclone passes, if the waters from the barrier layers are entrained, then it doesn't cool as you would expect from a cyclone churning the ocean. And there's been some papers by, I think, VSN Murthy, showing that sometimes as a cyclone passes, there is not only no cooling, but you may also get some warming. So barrier layer thickness corresponding to the salinity here is small, whereas it is generally small over the Arabian Sea compared to the Bay of Bengal, which especially during the post-monsoon season has thicker barrier layers, which there is also work by Ping Chang's group showing that barrier layers can affect the intensification of cyclones. Okay, looking just contextually for the globe, North Indian Ocean has a tiny percent of total number of cyclones, and the other basins are much more active. So North Atlantic, of course, gets lots of hurricanes. Northeast Pacific gets even more typhoons, cyclones, but Northwest Pacific is the most active in terms of producing about 30% of the total number of cyclones, whereas Arabian Sea has 2% and Bay of Bengal has 4%. Southern Hemisphere as a whole has only 29% and is less than just the Northwest Pacific. So there are various reasons why that happens. Most of you are probably aware of the genesis potential for cyclones, which looks at low-level relative vorticity, mid-tropospheric relative humidity, and the mid-tropospheric instability, which is the temperature difference between the 50 hectopascal and 500 hectopascal, and S is the vertical shear, which tends to inhibit cyclogenesis, so it's in the denominator here. So this is for low-level vorticity being positive, so that you have cyclonic seeds available, and mid-tropospheric humidity is loaded up, and the instability is present. Okay, otherwise GPP is 0. There are new ideas from the Chinese group, which also includes total heat content, cyclone heat potential in the ocean, tropical cyclone heat potential, in the ocean, which they argue captures some of the things better, and I like it as well. So just keep that in mind. ACE is a concept defined by Kerry Manuel, is proportional to the square of the maximum wind speed of the cyclone, as you can see here. It's calculated by summing the squares of the 6-hourly maximum wind speed in knots for the duration of the cyclone when it has a wind speed of greater than 35 knots or higher. The number is divided by 1000 to make it more readable and easy to interpret, but there is also the power dissipation index, which is proportional to cube of the maximum wind speed of a cyclone integrated during its life cycle. Okay, so this is just pre-monsoon and post-monsoon cyclones, tracks of the cyclones over 1980 to 2019. Pre-monsoon, post-monsoon. Black contours tracks are for cyclones with maximum wind speeds less than or equal to 95 knots, so category 2 or lower. Red colors are for cyclones with maximum wind speeds of greater than or equal to 100 knots, so category 3 and higher. Okay, so you can see that pre-monsoon has fewer numbers of cyclones, especially over the Arabian Sea, and there's been paper by Murakami and the GFDL group showing that the anthropogenic warming is increasing the post-monsoon cyclones in the Arabian Sea a lot. And there are other arguments as to why the Bay of Bengal will not have as strong a trend as the Arabian Sea, which we will come to in a minute. But you can see that the steering winds are different, so the tracks are also somewhat different in the post-monsoon compared to the pre-monsoon, right? Sea surface temperatures prior to the cyclones obviously are warming in the pre and post-monsoon in both basins, but both basins are warmer during the pre-monsoon than in the post-monsoon, as we already saw, because the northeasterly winds bring dry continental air and cool both basins in the post-monsoon season, whereas in the pre-monsoon season southwesterlies haven't set up yet, so both basins are significantly warmer. Looking at a scatter plot of maximum wind speed in knots and accumulated tropical cyclone heat potential during the period of 1993 to 2011 in kilojoules per centimeter squared per day in the Bay of Bengal. Cyclones formed during La Nina, El Nino, and negative Indian Ocean dipole, which has warmer sea surface temperatures in the eastern tropical Indian Ocean, and neutral years are marked in blue, red, green, and black circles respectively here. So La Nina in blue, El Nino in red. You can see that wind speeds are weaker typically for El Nino cyclones compared to La Nina cyclones, and there are many that are rapidly intensified, mostly during La Nina, something to keep in mind. And there are just a few neutral IOD, negative IOD cyclones here in terms of accumulated tropical heat potential. So you can see that the accumulated heat potential and wind speeds are lower for these, and there is one negative IOD way out here with some wind speed which has to be looked at more carefully from this paper from Girish Kumar. So I am kind of giving you a very brief summary. You need to read this paper and the papers that are synthesized into this review. Okay, so there is the question of the trends and trends in rapid intensifications as well associated with warming. Attribution exercises haven't been done very systematically, so I would also be careful about that, especially in terms of whether there is a decadal cycle the data going back in time is not good enough to figure out if there is a systematic decadal cycle in the cyclones over the North Indian Ocean. Okay, obviously you expect cyclones to induce sea surface temperature cooling, so Arabian Sea pre-monsoon and post-monsoon, you can see that the pre-monsoon cooling is larger. The yellowish colors here are from Neetu Singh's paper, which used cyclone winds on an ocean to look at how the cooling happens, and you can see that compared to observations, the models tend to produce much more cooling, and there is not much difference when they look at the two periods, 1978 to 2007 and 1998 to 2007. So the post-monsoon Arabian Sea cyclones don't seem to cool as much here, which has to be reconciled with the increase in the number of post-monsoon cyclones. So just keep that in mind. And Bay of Bengal pre-monsoon again is much larger cooling compared to the post-monsoon Bay of Bengal cyclones. These are details that have to be looked at much more in terms of vertical structures, systematic wind speed, maximum wind speed differences, and how together they are determining the air-sea interaction. This is the change in SST after the passage of the cyclones. As you can imagine, when you go from category 0 or 1 to category 2, there is a significant jump in the cooling, but after that the cooling is not much more, basically because the cyclones tend to use up the energy already when they intensify, and they are moving, so they're not sitting at the same place. So these are composite change in SST due to cyclones in the North Indian Ocean during 1982 to 2019. Different periods are used basically because it's synthesis of previous studies mostly according to cyclone categories. Based on the maximum sustained wind speed, the cyclones are categorized as category 1, 2, 3, 4, 5. You can look up the wind speeds. Okay. I don't think I want to say more about the details there. So main point I would make is that there is a jump and then there is a slight increase as the cyclones get stronger. You expect a chlorophyll response as well, which was done by Kutipurat in 2021. You can see that if you look at typhoons and hurricanes in the Atlantic and Pacific Oceans, the chlorophyll responses tend to be much more systematic than over the Bay of Bengal because of this complicated vertical structures, which are largely related to the local freshwater forcing from rivers and from precipitation. So one has to always remember that. Okay, so accumulated cyclone energy has some interesting comparisons as well. So they're looking at 1980 to 1999 and 2000 to 2019 just to see whether the more recent decades have any special trends. So you can see that the pre-monsoon Arabian Sea shows a significant increase in accumulated cyclone energy, and also similarly a proportional increase in the post-monsoon cyclones. But surprisingly, the Bay of Bengal has a slightly lower accumulated cyclone energy in the recent decades, whereas the post-monsoon shows a slight increase. So Bay of Bengal and Arabian Sea are remarkably different, which has to do with the background states themselves in terms of SSTs. When the SSTs are so close to the convective threshold as it is in the Bay of Bengal compared to the Arabian Sea, attempts to warm it tend to create more convection, which you think would give you more cyclogenesis potential, but there are other details that matter, of course, in terms of energy being dissipated away by convection and so on. So I won't go into the details, but you can read. But there is a paper by Bidut Bikash Goswami which argues that the monsoon trends are likely influenced by Bay of Bengal warming, because Bay of Bengal tends to be warm on average, and that means its response to attempted warming, let's say from anthropogenic forcing, tend to be different than the Arabian Sea, which is much cooler. Okay, so lifetime maximum intensity of cyclones also shows that, of course, that has to correspond to the accumulated cyclone energy. Pre-monsoon shows a significant increase here of whatever percentage you can see here, and similarly for the post-monsoon over the Arabian Sea. But Bay of Bengal pre-monsoon shows a slight decrease, and almost similar in the two periods considered here for the Bay of Bengal. So these have to be considered as well. To summarize, they use these schematic figures highlighting some of the key open ocean processes in the asymmetric response of the ocean cyclone interactions over the North Indian Ocean. So we are looking at depth in the ocean and the atmosphere. So weak mixing, weak inertial current, and weak entrainment create weak cooling and less saline conditions. And when the cyclone passes, you have strong inertial current, strong entrainment, and surface cooling happening. So weak wind stresses and more rain give you this warmer, less saline conditions, and post-monsoon you have again less rain but stronger winds, so you again have strong cooling and more saline conditions. This is kind of considered as key open ocean processes in the asymmetric response of the ocean atmospheric interactions over the Bay of Bengal. So you can also consider this as a reason for asymmetry between Arabian Sea and Bay of Bengal, because Arabian Sea is more saline and more evaporative basin, as opposed to Bay of Bengal, which has much more freshwater forcing and barrier layers. So the role of the barrier layer is not systematically considered yet, which would be an open question for now. So this is finally the schematic highlighting some of the key processes involved in ocean cyclone interactions in the North Indian Ocean. Quantification of the ocean temperatures, translation speed, and ocean cooling is based on the studies that are discussed in the paper. So here you have warm ocean temperatures in the range of 27 to 31 degrees centigrade, and the question is how much warmer these are getting, and whether the response to warming is different in the Arabian Sea versus the Bay of Bengal. Mean conditions are also different in terms of vertical shear in both pre and post monsoon. So you also have warm core eddies. So strong heat flux transfer from the ocean to the atmosphere. So oceans driving the atmosphere. Intensification of the cyclone, which is obviously fed from the available cyclone potential in the ocean. So effect of cyclone on the ocean is done through multiple channels here, where you have influence of cyclone characteristics determines translation speed, let's say 17 kilometers per hour here, whereas in the low translation speed you have 9 kilometers per hour. So you have two categories there. So you have strong ocean cooling, 1.5 degrees centigrade to 4 degrees centigrade, as we saw already. Strong phytoplankton blooms here, whereas if there is a high translation speed, the cyclone moves past fairly quickly, so the ocean cooling in fact is weaker, only 0.4 degrees C to 1 degree C. So if the cyclone is moving slower, it has more time to pick up energy, and there are broader implications, because it is generally argued that cyclones are beginning to move slower as the ocean is warming, because a warmer ocean is also providing more heat content to a deeper level. But this may not be necessarily the case for the Bay of Bengal, so this has to be looked at. Okay, so this here also comes effect of cyclone on the ocean also comes through influence of the ocean characteristics. So weak stratification and barrier layer in the Bay of Bengal, for example, would lead to strong ocean cooling, and a strong stratification and barrier layer would lead to weak ocean cooling and corresponding chlorophyll responses. So you also have cool ocean temperatures when they are less than 27 degrees centigrade, and cold core eddies, which would weaken the heat flux transfer from the ocean to the atmosphere, which tends to weaken the cyclone, and that is related to the strong ocean cooling that has already happened from, let's say, a slow moving cyclone, which reinforces the next cyclone that is coming in. So number of cyclones matter here as well, and that can also be important in terms of the Bay of Bengal versus Arabian Sea differences. So I'm just giving you a fairly brief survey of the article. There are many more details that you can look up, and many papers are cited which have lots of other details that are summarized in this review paper. So I'm going to leave it here. Wanted to just report this paper which just came out. Okay.